All right, so fill out these QR codes if you haven't already. And then this is a shout out. We have an event coming up, big event hosted by QSO, Friday, April 4th, 3 to 7 p.m. Spring into Quantum. So it'll be, I mean, all the details I'm not certain of, but we'll have some large, like some big speakers from industry, I think, and academia, and like a national lab. I think I go with 3 speakers. But you can go to this QR code for details. And then there'll be like a poster session throughout the day and into the evening. We'll have refreshments, snacks. So it should be a big deal. I'll definitely be there. It should be fun. Just let me know if you have questions. Okay, so this is today's outline. GPS is kind of the introduction, and then that gets us into how atomic clocks work, the types of atomic clocks, how these different types are different, and then other applications of atomic clocks that aren't GPS, and then we're going to compare the accuracy of atomic clocks. Yeah. So what is GPS? Wait, hang on a second. Let me get the laser pointer here. How do I do this? There we go. That's better. So the GPS, it provides users with P&T, positioning, navigation, and timing. And I don't remember where I read this, but the idea of GPS is like it's managed by the U.S. government. At least, I guess the U.S. version, and there's probably worldwide versions, but anyone with a GPS receiver can use this system. Like you don't have to, have like I don't know, like a secure access or something, because it's the U.S. government and they're all secretive. But it's available for anyone to use worldwide. GPS consists of 3 segments: the space segment, control segment. Those are operated by this U.S. Space Force, and then 3, the user segment. Like I was just saying, it's anyone can use it. See if I'm missing anything. Nope. All right. Yeah. So here's just some quick facts that we'll run through. You only need 24 satellites needed for GPS, but there's like 31 just in case we lose some or they stop working for some reason. They fly in this medium Earth orbit at an altitude of 12,000 miles. So the control segment facts. We have a global network of ground facilities that are going to track GPS satellites, monitor transmissions, perform analyses, and send commands and data to the constellation of satellites. So you can see here all these different stations, and they're described here. So you have the master control station in Colorado, alternate master control station in San Francisco, maybe. And then you got command and control antennas. You got monitoring sites. So, yep. Question? Why is there just this about all the other continents, South America, Africa, Asia, Australia? Well, the short answer is that this was developed by the U.S. I guess I don't really know all the details, but I feel like they only need so much everywhere else to have like full planetary coverage, But even like they would still be planetary coverage like all these other places, like a lot less like control stations, or like with the North America get like much better coverage. That's a good question. I'm not sure. Why are a lot of them in like small islands, like like what? Sorry? Small islands. Like if they're doing ascension. Right. I guess it's just Hmm. It's probably partly like, what the US has uh reign over, like you can't put something in China because, you know, politics, but uh yeah, so it's just to get an even like as spread out coverage as you can get, I guess. Like, you have ocean and that's like a lot of ocean and then like you need coverage in the ocean for, I don't know, people like captains that navigate ships. So they just got to pick something. Yeah, I don't know a lot of details about this stuff. So, what is a clock? Give me some examples. Yeah, a clock on the wall. You got a clock on your phone, right? Um, what's like a historical example of a clock? Like what was used before the phones, um, in like I don't know, big mansions or something. Yeah, like Big Ben, like pendulum clocks, like a grandfather clock, right? Um, and then you also have like wristwatches. Um, so what is a clock? So a clock is a mechanism that oscillates, and then secondary is a device that measures oscillations and displays the time. So the problems that we have with non-atomic clocks is that the oscillation mechanism is never exactly the same. Um, we'll get more into that a bit later when we compare all the accuracies. It's pretty cool. Yeah, the time is never perfectly in sync, and they're just inherently unstable. Um, okay, yeah, I can mention this too. So, right, so humanity began keeping time with like the stars and planetary bodies in our solar system. That's how we have, um, um, 365 days in a year, and you have four seasons and all this kind of stuff. Then we decided to use pendulums. Um, and both of these are gravity based and aren't perfectly consistent. I think especially because like the the force of gravity is like pretty small compared to like um, electrostatic force or magnetic forces. So they just weren't that great. But then we found that we can use a quartz crystal to keep time pretty well, and that's what powers a lot of like wristwatches. Uh, mhm. Uh, I do not know exactly. Um, if I had to guess, it's some kind of piezoelectric kind of thing, where so piezoelectric is like you have piezoelectric materials, where if you apply a voltage across the material, it will change its structure. Like it'll get a little bit longer, a little bit shorter. So I'm guessing that's kind of there's some detail in there um, that provides some oscillation, but I'm not exactly sure. So okay, so let's make an atom into a clock because atoms. Well, actually, we'll get to that in a second. Or yeah. So like we just said before, we need a mechanism that oscillates. And to do that with atoms, we can look at the energy transitions. We can oscillate those. So, for example, from the ground state of the hydrogen atom to the first excited state. That's a really rough example, and we'll get more of the details later. But uh, these are the most stable and precise measures in the universe. So, two, we need a device that measures oscillations and displays the time. So, what good is something that oscillates if you can't measure it, right? So we can shoot light waves into an atom, and then we vary the frequency of these light waves until like the most gets absorbed by these atoms. Um, so for a quick example, you might be wondering why I have a picture of a swing up here. Uh, so if you have like a resonant frequency, like pushing a child on a swing. Like if you're pushing them at the resonant frequency of their like swing, they're basically a pendulum, right? So the resonant frequency of the pendulum, then they're going to go higher and higher each time. That means you're pushing them as they go through. You're pushing along with the direction of motion. It's the same idea in atomic clocks. So if you tune a laser to the exact right resonant frequency and shine it on a group of cesium atoms, for example, the group of atoms will get collectively more and more energized because you're promoting them to this higher energy state. So it's the same idea. Does that make sense? How is that oscillatory? Yeah, that makes sense. I think so. I explain it in the second type of atomic clock that we're about to get into, and that uses quantum superposition. So it'll, which honestly, like I know what superposition is myself, but apparently the way it works is that it oscillates between like the superposition states. But I don't know how that works. You know what I mean? So yeah. So sorry, I don't know all the details here, but I think it'll start to make a bit more sense if what I just said doesn't make sense. So don't worry. So before we get into the details, let's review the fundamentals. And before I do that, any questions so far? Good. All right. So just kind of review of electromagnetic spectrum. So the idea here is that if you look at this formula, you've got energy of light, and then here you can equate that to basically the frequency, and then there's just a constant in front of it. And then over here, even further, you can get the wavelength of light, and then you have two constants up here. So essentially, you have energy, frequency, wavelength. These are all, like in the context of today's discussion, these are all kind of synonymous. They're kind of the same term. So, if you have light that is, an X-ray region, it's at some wavelength of X-ray light. It also has a unique frequency associated with that and a unique energy that no other, wavelength of light has, right? Is that good with everyone? And then here we just have the simple Bohr model of hydrogen. And the point I want to make here is that the energy levels of hydrogen are discrete. So you can only take in certain energies to promote to the next more excited levels. And you can only emit certain frequency, certain energies as photons. So yeah, so to reiterate, energy, frequency, and wavelength here are going to be synonymous. So yeah, and then the idea here is also that light waves can occupy any energy, any frequency, any wavelength that they possibly want, anything. But when you go to atoms, there's very discrete allowed values of wavelength of photons that can interact with it, right? Does that make sense? Okay, good. So there's 4 major types of atomic clocks. And I'm just now realizing I didn't really go into the chip scale atomic clocks, but whatever. We talk about other things anyways. So types of atomic clocks, we've got the beam clocks, which were first invented in 58. And we have fountain clocks, which is very similar to that. perfected in 1999, and then early 2000s we have optical clocks and chip scale atomic clocks. So basically, for beam and fountain clocks, we decided to use cesium as our atom of choice, and we'll get into the details. Fun fact, I spent last summer, 2024, working at NIST, which is the National Institute of Standards and Technologies. And we got to go on a little tour of the NIST beam atomic clock, which is the picture I took here in the bottom right. And I took a picture of this little diagram. You can see my thumb. And then this is the official picture up in the top right. So NIST had the, I guess, first successful, or they standardized the definition of the second with this apparatus. So let's just kind of walk through it. So on the left here, actually, no. So this whole tube is a vacuum tube. It's very important to have a vacuum tube so you can, isolate just your cesium atoms. And then you have your source of cesium atoms in any energy state they want to be in. Then you shoot them along this thing with probably some kind of electric field. And then on their way, you have laser A, which is going to I think it's going to laser cool the atoms by putting them into their lowest energy state. We'll get more into the laser cooling later. And then you have this microwave cavity where you're inputting some frequency that will interact, some frequency that's either very close or exactly at this frequency of the energy transition in cesium. After you do that, the cesium atoms continue and they hit laser B, which then puts atoms in, or it causes any atoms that are in the excited state, excited by the microwave cavity frequency that we just input. And it causes those to emit light, which is then detected by this detector here. Does that make sense? Some of the other details here aren't so important right here. And then we'll look at this for just a second. So like I said before, I was saying that the hydrogen atom, you can think of atomic clocks as the energy transition from ground to first excited state. However, in reality, it's a much more precise energy transition. So what you have is in the cesium atom, you have all sorts of electrons and on the inner orbits, and then on the outer you have a single valence electron. If you remember this, any atoms in this row or this column of the periodic table have one valence electron. So this single valence electron will, you can imagine it's like a bar magnet. There's electrons have spin, which you can think of as a bar magnet. Electron spin is really weird and it's hard to think about. So it's a bar magnet, all right? So basically you'll get an energy transition from flipping the direction of this bar magnet because that's going to interact with the internal bar magnet. So that's what we're looking at here. So here's the nitty gritty. You have this concept that the outer electron orbiting the nucleus can be modeled as an electrical current, which you can see down here. So this is the proton, this is hydrogen. So just imagine hydrogen here. And then the electron is orbiting around. In the point of view of the electron, the proton is actually orbiting it. And then that leads to this idea that you have this current going around, essentially. And if you know a thing or two about electromagnetics, then that's basically Ampere's law. So an electrical current on a closed path generates a magnetic field. And that's where we get the idea, that picture of like these bar magnets flipping. Well, not flipping. So then if an electron spin flips from up to down, or vice versa, the energy of the system changes. So this is known as like a fine structure concept. And I'm very fuzzy on all the details with these S, L, and like J. These are all like angular momentum vectors, but yeah, you can feel free to ask me questions later, maybe. So yeah, are you with me at least a little bit? Cool. So, sorry, let me move this. All right. So we have the cesium-133 isotope. The energy transition we just discussed has a resonant frequency of 9,192,631,770 hertz. And if you're unaware, hertz is basically just like, that's the number of oscillations happening per second. Yeah. So different isotopes will have different resonant frequencies because you're essentially removing or adding a neutron with these different isotopes. I think there's something like 30 different isotopes for cesium. Right. So the uncertainty of measurement with this, using this resonant frequency is much smaller than the uncertainty associated with the astronomical observation-based oscillations or the like pendulums that use gravity. So, and you can see that with just how many significant digits you have here. You have like 9 or 10 significant digits. Okay, on to fountain clocks. So, like I said before, these are very similar to these beam clocks, but I guess you could say they're just a little bit more modern. So again, yeah, I was able to tour this one too. This one's actually like in a lab. So it's like, you know, a bit more, I don't know, messy, I guess. So the key design is that it's still using this same isotope as the beam clock, but now we've got cryogenics and we've got laser cooling. So the cryogenic means basically it's close to absolute zero. You're cooling it down a lot. And the laser cooling system will get your cesium atoms even closer to absolute zero. This is important because if you have, I mean, you think about like infrared imaging, where you can like, if you have an infrared like camera or something, and you like look at people, they're like red, they're like different than all the surroundings. You know, it's this idea of like black body radiation, if you guys know that, where basically if something has a temperature, it's going to emit some light. And you don't want any spare light if you're trying to analyze this really specific energy transition in cesium. So yeah, so a fun way to think about laser cooling is to, if you had a rolling bowling ball and you were to slow it down with a bombardment of ping pong balls. That's kind of the idea here. So in the analogy, the bowling ball is these cesium atoms that are big and bulky, and then the ping pong balls is the laser, like the photons. Okay, so yeah, then there's these specific design steps which we'll walk through. So here's the picture on the bottom right. We have 6 lasers that cool the atoms on the bottom. So you have the 4 down here, you have 1 down here, and 1 at the top. So after you cool them down, they make their way up. This microwave cavity here in the middle is it's essentially the same as like this microwave cavity, like the same purpose, where you're injecting your own frequency into the system, and then this allows it to go into this quantum superposition state, which then oscillates in time at that resonant frequency above the cavity. And then the atoms make their way back down after about a second. And then the microwave cavity applies a second pulse. And then the second pulse is essentially like, you know what frequency you're applying the second pulse at. And then it's going to interact with the cesium atoms, and then you'll end up detecting, which cesium atoms were excited by that in some way. And so with this second pulse in the microwave cavity, you apply some frequency, and then the cesium atoms essentially tell you how accurate that frequency was to the true cesium atom frequency. So it's like that's kind of how you tune your ideas. Like you apply the frequency that you think is the resonant frequency of the cesium atoms, but you're not quite there, and you see that there's there's this difference in the frequency. So then you change the frequency you applied and repeat until you get really low error. So then after this, I kind of skipped over the fifth point, but there's a probe laser that hits the cesium atoms, and then there's a detector that detects which atoms were affected. Does that make sense? Yeah, question? Yes, but it gets interesting with general relativity, because if you might know, we'll get into this in a little bit too. But basically, if you're at different elevations on the Earth's surface, you're going to have a different gravitational field applied to you, and that means that time runs slightly differently at these different elevations. Does that kind of answer your question? I don't know if I did. Okay, so, but how exactly is the the fountain clock different? Well, it's cryogenic, it's laser cooling, we know that. And there's a full second that passes between the two microwave pulses that we put in the microwave cavity. So the cesium atoms went up, and then they went down. During that time that they were above the cavity, there's 1 second that passes. However, on the other hand, with the beam clock, it's at room temperature, so you have all sorts of infrared radiation or black body radiation, no laser cooling, so it's like you're going to be less accurate because of that. And then you only have milliseconds between the two laser pulses, because you're shooting the cesium atoms through this thing at, I think it's like 1,000 miles per hour. Yeah, so with more time, you have more accuracy, and with cooler temperatures, you have more accuracy. How can we further improve the accuracy and stability of atomic clocks? Optical clocks. So the idea with optical clocks is that you can use higher frequency energy transitions to gain more significant digits in measurements. So before, we were looking at like 9 gigahertz. That's like 9 billion hertz. With optical clocks, the frequencies, actually, I'm not sure what the exact values are, but the frequencies are larger than 9 billion hertz, which means that you have more accuracy, more precision you can work with. So the first optical clocks were made with hydrogen, calcium, and mercury. And then I guess what has proved to be most effective since its inception are aluminum, strontium, and ytterbium. I think aluminum takes the cake, if I remember right. So what is the common theme of all these atoms? Any guesses?
They have a lot of like valence electrons.
You said they did not have a lot
Like
of.
helium has
Right.
two,
Uh-huh. And Mercury has two. Yeah. So yeah, I mean that's true. They all have few valence electrons. Um, and I don't know exactly how this process will work with the optical clocks. Um, but I mean, all I was searching for with that question was that these are atoms that will have some kind of energy transition that's going to be in the optical range. So when you look at the electromagnetic spectrum, again, uh, you've got radio, microwave, infrared, ultraviolet, X-rays, gamma rays, and then right in here is visible light. So visible light means optical. It's vice versa. That's the same thing, I guess. Um, so then you can see all these lines for. So I would guess that these atoms here on the left are what they use for the beam and fountain clocks. And then when you're getting close to the visible light or optical range, then you have the stuff that we just looked at. All good? Okay, so let's make an atom into a clock. Let's bring this back from the very beginning. So we need a mechanism that oscillates, and like we said before, atomic energy transitions can oscillate, and these are very stable and precise, most in the universe. And to measure these accurately, in turn, we need very precise laser frequencies. If you're going to measure something that's incredibly precise, has like optical energy transitions, then you need really precise frequencies that you're inputting, like in the microwave cavity before. And two, you need a device that will measure these oscillations and display the time. So, like we said before, we can shoot light waves into an atom. We vary the frequency of light until it gets absorbed, and we use a frequency comb to measure. So I think the idea of optical clocks was proposed like I don't know, like relatively long time ago, maybe 60s or 70s or something, but they didn't have precise laser frequencies, enough precision in these laser frequencies to work with them and to be any better than the fountain clock. And then frequency comb, I didn't get a lot of time to look into that, but that's like something we can look into once I finish here in a few minutes. If you guys want it, we can just start looking on the web. So yeah, so I guess that's it for optical clocks. Uh, we can any like questions that aren't too in depth right now. All right, yeah.
also, so I don't remember they measured time. You make the
Um, I think essentially when you have the frequency, you're inputting these frequencies, and you can convert this frequency to time. Because what's the conversion? It's just you just take the reciprocal of frequency and to get time. Yeah, I don't know the details there. I see what you mean.
to get 1 second when you just like wait and like you wouldn't just wait until you had like 12 gazillion oscillations and then you're like, yep, we're all good at the second.
Um, yeah, I mean that's essentially what you're doing, right? Um, yeah, I don't know. It's kind of weird to think about. Okay, so let's return to the GPS thing. I didn't really touch on how atomic clocks are used for GPS. So I copied it from Wikipedia. So so we can just read through it together. So the GPS satellites carry very stable atomic clocks. I'm not sure which kind, but I would guess some of the smaller ones. So maybe like optical. I think that can be smaller because the beam and fountain are a bit bigger, and you have cryogenics and complicated stuff. Excuse me. So these clocks are synchronized with one another, and they reference atomic clocks that are on the ground control stations. Um, that makes me think of your questions about why you have all these different control stations in random places in the world. I think maybe part of it is they put it at different elevations to study general relativity. Um, so, there might be some in Hawaii on the top of a volcano, and you might have some at sea level in San Francisco. So, um, any drift of the clocks aboard the satellites from the reference time maintained on the ground stations is corrected regularly. And that's essentially Einstein's general relativity. Since the speed of the radio waves is constant, the speed of light, this is more kind of general relativity stuff. It's constant and independent of the satellite speed. The time delay between the satellite transmits, between when the satellite transmits a signal and the ground station receives it is proportional to the distance from the satellite to the ground station. With the distance information collected from multiple ground stations, the location coordinates of any satellite at any time can be calculated with great precision. Um, and then each GPS satellite carries an accurate record of its own position and time and broadcasts that data continuously. So, yeah, based on data received from multiple GPS satellites, an end user's GPS receiver can calculate its own four-dimensional position in space-time. Four dimensions being the three physical dimensions and time. However, at a minimum, four satellites must be in the view of a receiver for it to compute four unknown quantities. Yeah, that makes sense. Helpful. I thought that was pretty neat. And I thought I probably couldn't write it in a better, well said manner. So just straight from Wikipedia. So other applications of atomic clocks. We have geodesy, which is basically the study of the shape of Earth's surface. And I've got some notes I'll read here. So because the presence of gravity affects the rate of time passing, clocks closer to sea level actually tick slower than one on Mount Everest, which means that physicists can use these clocks to monitor the shape of our planet. There was one other thing. Some researchers think that this capability could help them more accurately monitor the change in sea level. And then we have very long baseline interferometry. This is, you're going to use atomic clocks at each station you have for this interferometry. You have stations all around the Earth. This is the technique they used to image the M87 black hole back in 2020 or 2019. You have to have synchronized clocks to know you're getting synchronized data from the imaging. And then, like I've been saying this whole talk, we're going to test Einstein's theory of general relativity. And then, so if you guys have seen Interstellar, basically, when they go close to the black hole, they go to a planet that's close to the black hole. An hour on Earth is like 7 years on this planet. Or no, the other way around. An hour on the planet makes 7 years of time go past on the Earth. And then when he went into the black hole at the end, spoiler alert, like 100 years went by on Earth or something. So yeah, and then precise timing for space travel and space navigation, basically just to help spacecraft orient themselves and navigate autonomously, and then maintain coordinated universal time (UTC). Um, Labs like NIST all over the world share their data amongst each other to find the most accurate definition of the second, also taking into account Einstein's general relativity. What else do we have here? Something else. Yes, this is the fun part. So clock accuracy comparisons. So we start with a grandfather clock that's based on a pendulum. I guess there's a spring that's gonna help the pendulum stay swinging. So you have to rewind this spring once a week. I couldn't find information on how accurate it was, but that helps. So you're on the time scale of a week. And then with a quartz crystal clock that you have in your wrist watches, under 15 seconds per month. So you're gonna be inaccurate by just under 15 seconds a month. And then if you go to NIST 7, that's that's the first beam clock that I showed you, and it uses the cesium atoms or isotopes. That's gonna be inaccurate by under 1 second and 5 million years. Then the next, the fountain clock, under 1 second and 20 million years. The same idea here as we keep going. Present day fountain clocks, 1 second in 100 million years. And then Mercury, the very first Mercury optical clock made by NIST, 1.5 billion years, 3 billion years, 30 billion years. So yeah, it gets pretty nuts here. There was a fun fact that I don't remember. Oh yeah, so stuff like these fountain clocks and optical clocks, they don't run continuously. They like when you think of a clock, it's running continuously, right? But these act more as like a tuning fork for like our everyday clocks. So I think maybe I don't remember what the article said, but basically, we still use this clock, and we have wristwatches and all this, which aren't perfect, but we can go back to this standard that is perfect, and reset our clocks to match it. So that's it. Questions, comments, concerns, anything you guys want to discuss more in depth? We have 8 minutes.
When will they give up on the?
I don't think they ever will give up. Yeah, I don't know.
1 second. It was billion years, like
Yeah, longer than the age of the universe. Yeah.
have to be more than like
Hmm. Yeah.
like I think like is there any context where you need like better than like effect or something like that?
Um, one thing that I do remember from the research I did, like space travel, I think maybe because if you think about it, if you're estimating, I don't know the details of how this works, but if you're finding the location of your spacecraft, say like Voyager 1 or Voyager 2, that we basically ejected out of the solar system, they're going faster than any other like man-made spacecraft. If your definition of the second isn't very precise, then you won't know exactly where it is in 30 years or something. You know what I mean? Like you'll have a wider range of uncertainty on like the distance it's traveled. That makes sense?
Okay, the big time scales and big like distance scale
combined. There's in modern physics, there's this idea of like length contraction and time. So, I mean, the time, I forget what it's called, time dilation. So both of those are like the idea of general relativity, I think. So I'm just saying, I'm making the point that like length and time kind of go hand in hand when it comes to physics. So, yeah. You had a question, Ian, right? Yeah, I think it's possible. It's just like it's they consume so much power. It's just like not worth it. Yeah. So I mean that kind of gets back to Ben's point. It's like, yeah, they're useful in some ways, but we don't need to use them all the time. We're pretty good with what we have already. The stuff that doesn't consume a lot of power. I'm kind of curious for myself how these frequency combs work. So I'm going to pull up an article on that. Okay, the short answer, what is that? It's a way that you can measure these really precise laser frequencies. So, okay. So it was optical clocks where you use this frequency comb, right? And we said that for optical clocks, you're using really, really precise laser frequencies. So with these really precise laser frequencies, you need some way to measure it and actually put it into like your electronics. So that's essentially what a frequency comb does. I do not know. So let's pull it up.
I'm doing like EC. I'm wondering like what circuit element.
Right. I'm curious as well. So this was the article on the optical clock. Yeah, so count the wave peaks of that laser light with extreme accuracy, something beyond the reach of conventional electronics. So then the breakthrough came in 1999 when they invented the frequency comb. So they say that they're rulers for light that can translate visible light frequencies into microwaves that electronics can read. Let's find out. So, okay, so it's converting some frequencies of light into different frequencies of light. Maybe we can, I think the idea is it's taking this, a very small range of frequencies and it's translating it to different frequencies and like blowing it up so that you can see all the details more. That's my guess, but I'm not sure. Oh, here we go. Let's watch a video.
This is a box, but it's not just any box. It's a special box, a Nobel Prize winning box. This box is on telescopes, discovering planets and studying stars across the galaxy. It's in this atomic clock, measuring time in millions of billions of seconds and helping us navigate via GPS. It's measuring greenhouse gases in our atmosphere. And here it is again, in a breathalyzer, finding traces of disease. How can a simple box do all these things? The box is more than just a box. It's an optical frequency comb. It's like a ruler that measures light. Light travels in waves of different colors or frequencies that all jumble together. An optical frequency comb can straighten out that jumble, turning each frequency into a single spike, like teeth on a comb, distinct, evenly spaced. Using the comb, scientists can easily pick out individual frequencies from the jumble. Similar to light, atoms, molecules, and ions also have unique frequencies, almost like fingerprints, which means the possibilities of what these frequency combs can do are constantly expanding. Want to learn more about how frequency combs do these incredible things? Visit www.nist.gov/physics.
Yeah, exactly. That's what I was gonna ask. So that's if you, there what they said here. Let's go back to the picture. You're going from uh, these waves, these light waves, which are based in time. Um, if you were to plot like uh, what the physical like, if you were to plot the electromagnetic waves of light with respect to time on a graph, that's what you would get, right, on the left. Um, and then uh, you can take this jumbled mess and convert it into the Fourier domain, which is basically a frequency domain. So you start in the time domain on the left, and then you go into the frequency domain. So then you're seeing the individual peaks that represent different frequencies. So that's pretty neat.
Makes a difference. All like this technology that allows you to transform the that's the crazy part of the technology. Way transform the wrong.
Right. Yeah. The math has been there for a while. It's a good point. Yeah. I don't know if this. I don't think this really goes into the technical details here. Oh, maybe it does.
In very minimal detail about like how it was actually done.
Yeah, like the circuit. Yeah.
I wanted to see.
Oh.
Oh well.
Next. Oh. Well, they showed the like crazy like new experiment setup, but not the simple one. Oh well. Well, it gives you a good idea, I guess, how it works at least.
Mm-hmm.
I guess I'll just conclude here. Um, so this is kind of, well, I don't know if this is very relevant, but I'm trying to tie this into like a lot of talks that I do this semester. Um, so like this was the first quantum revolution was, 1900 to 1927, where all these physicists came up with these theories that described how stuff works in the quantum world. And in 1925, Heisenberg and Born basically made matrix mechanics, essentially math that describes all the quantum mechanics that people had theorized before. And so people are calling that the beginning of quantum. So now, 2025, 100 years later, they're calling the International Year of Quantum Science and Technology. So, yeah, it's a big year for quantum. That's all I have. Lots of applications now. So it's almost like today is this second quantum revolution, where in the first quantum revolution, people were inventing theories and stuff that explained how things worked. But now in the second quantum revolution, we're using that for real applications, and these are some of the applications. And there's lots of funding going into it.